I think the meeting already began, so we started the webinar. So I welcome everyone. Thanks for being here. Thanks for participating and being part of our webinar. I just checked the registration number, and I think with 355 registries, I would consider it as a successful webinar already before it had started. So I think we will be more and more people in a few minutes. Right now we have 103 participants with us. And I want to welcome everyone. My name is Lara, and together with Matea, we are our hosts, your hosts today. Both of us, we are part of the Young Professional Board of the ICOLD. Matea is the chair, and I'm one of the vice chairs. The agenda for today will be streamlined all the way down with the sediments. But first of all, we want to start with a small welcoming from the Lisa Bensasson. She's one of the vice chairs of the ICOLD, and she will connect the Chengdu Declaration with the topic of sediments for us today. After that, we will start with the topic of sedimentation by a keynote from George Annandale, leading us to a presentation from the current pilot projects which are out there on the field of reservoir sedimentation management by Marty Teal. And we will close the session with Christian Auel, professor in Germany, and also chair of the ICOLD Committee J, ICOLD Technical Committee on Sedimentation Management. And at the end, we have like around about 30-minute Q&A session for you. So we would like to ask you to gather all your questions around, maybe put them in the Q&A section, and then we can, just have a discussion on the topic of reservoir sedimentation at the end of our session. So thank you very much. And Lisa, I would like to ask you to start. You're on mute.
Good morning or good afternoon to everyone. Thank you, Matea. Thank you, Lara, for the introduction. And I'm now going to share the very, very short presentation. I don't want to take any valuable time from the esteemed speakers and the excellent audience. Like Lara said, I would like to point out what is relevant with sedimentation management in the Chengdu Declaration about dams and reservoirs for energy transition and climate change adaptation. And many of you might be asking, what does it have to do with sedimentation? So this is why I'm here to tell you about it. And just a look at the signature of this Chengdu Declaration, which took place in Chengdu last May. And the declaration looks like that. You can find it and download it from the site of ICOLD. And if we zoom in, we will see the title and we see the signatures. It has been co-signed with International Hydropower Association, International Energy Association, the International Commission on Irrigation and Drainage, the World Water Council, and the Institute, the Mediterranean Institute for Water. And it has the main sections, are about a changing world, the clean energy transition, climate change adaptation, which demands water storage provided by dams and reservoirs, some environmental considerations, and finally the recommendations. I'm not going to go through all of it, don't fret about it, but I am going to say why reservoir and storing water in reservoirs is so important, because right now the global population has skyrocketed from 1.5 billion in the early 20th century to nearly 8 billion today, and projections have it that we will reach 10 billion.4 by 2100. And this population rise directly impacts water demand, which could rise by 20 to 30% by 2050, which raises the issue of water and food security. You understand that feeding a population of 9.7 billion by 2050 will require more freshwater storage in order to avoid stress for up to 4.6 billion people. And the current global water demand of 4,600 cubic kilometers per year is 50% of which is used for irrigation. So unless freshwater storage is drastically increased, up to 1/4 of children will be living in water-stressed areas by 2050. Then we need to think about climate change uncertainty. Changes in precipitation patterns, increased evaporation rates, melting glaciers are expected to exacerbate water scarcity in many regions and increase the frequency and duration of droughts and the frequency or peaks of extreme precipitation events, with direct consequences of flooding. But so we understand that we need by all means to safeguard and expand water storage capacity, which is essential for securing water and food supplies in a changing climate. Effective water and sediment management are necessary to ensure a climate-resilient supply for drinking water, agriculture, energy generation, and environmental needs. And so this is why we find some messages and recommendations in the Chengdu Declaration that have to do with reservoir sedimentation, because annually around 0.8% of storage capacity is being lost due to reservoir sedimentation. And the rate of sedimentation is expected to rise in many areas where erodibility will worsen under climate change unless reservoir management and watershed measures are implemented. We also note that per capita storage capacity has been steadily declining since the 1980s due to population growth, sedimentation reservoir, and of course a decline in dam construction pace. And even when we consider the environmental impacts, we have to take sediment management into consideration. Through greater understanding of dams' impact and effect of preventive and mitigation measures, we can enhance their sustainability throughout the life cycle. In the recommendations, we find recommendation number 9, which strongly suggests that promoting sustainable water and sediment management is essential to preserve the functions of dams and reservoirs, considering techno-economical, environmental, and/or regulatory constraints. In brief, we say that we need to maintain effective water and sediment management. And what's next? Next is that we would like to ask all national committees, regional clubs, and of course YPF, that gives us a voice here, to disseminate the messages of the Chengdu Declaration and to pass on the messages that we have very good examples, very good case studies cases where all this is beneficial, like Lake Erkini in Greece, which is a Natura preserve, a Ramsar Convention site, and provides flood protection, sediment control, irrigation, and the small hydro. Thank you all for being here and for passing on the message.
Thank you, Lisa, for this short introduction on the Chengdu Declaration. And I think, like, I've been with the Chengdu Declaration now, or the presentation on the Chengdu Declaration for the second time, or maybe third time, and I still think it's one of the best and most wanted or most needed declarations we need in the current times. So thank you for spreading out the word, and everyone who wants to get more information about the Chengdu Declaration, follow the link, check out the materials which are out there, and also spread the message. Thank you. That leads us to our keynote on the topic on reservoir sedimentation and sustainable sediment management strategies. And George, I thank you for being here and giving us the keynote. And I just want to give a quick introduction to the audience. So you're a consultant and one of the leading experts in the field of reservoir sedimentation. And you're one of my favorite authors when it comes to basic knowledge on reservoir sedimentation. So just a short advertisement, I would say. The book you've written together with the World Bank and co-authors is Extending the Lifespan of Reservoirs. And I just received a hard copy at the last event, the Hydro 2025. And I got fully invested. I read it all through, and I think that's one of the must-reads for everyone who's interested in sedimentation in reservoirs. So I will give the stage to you. You're on mute.
Thank you very much, Lara. I have about 40 hard copies here in my study. So anybody who would like a hard copy, let me know. If you pay the postage, I will send you a hard copy. But let's just then start. I think what I'd like to do is just to reflect on the whole topic. Lisa has presented the Chengdu Declaration, and I must say that more than 30 years ago, so shows my age, I guess, when we started to promote the concept of sustainable development and reservoir sedimentation management, it was a concept that was not gladly accepted in ICOLD by many of my colleagues. And they thought that dam design is the only thing that's worthwhile. So having this declaration signed in Chengdu is something that is really gratifying. I just need to start with that. And thanks for presenting that whole concept. I highly appreciate it. Okay, so what I would like to do is just to recap on why we are really looking at reservoir sedimentation management. And I do this under the topic of everlasting abundance of water, looking at sediment, climate change, and sustainable development. So let me just close this thing. So why is this not moving on?
So just a short interruption from my side. If you try to share a presentation, I cannot see it, and I think Matea is not seeing it either.
Really?
We just see a blank space.
I can see it. I can see it.
I can also see.
It's a light blue.
All right. So I think the problem is on my side.
I could, if you have it on a different screen, it happened to me, you have to click on that screen and not on the screen that is in front of you.
I just saw a message in the chat. There is someone else not seeing it. George, would you please stop the sharing?
It seems like George
restart
is
it?
frozen. It seems like George is frozen. Maybe he needs to
reconnect.
George, if you can hear us, we see you as being frozen, so you might need to drop and reconnect.
Can we continue with the other presenter? And in the background, we solve the issue with George.
Yes. Okay.
We could wait for some seconds, but if not, I don't know, Marty, if you're prepared, I guess.
Yeah, I can jump in, but let's wait a few minutes or a few seconds for George, see if he's able to reconnect.
Yes. Okay. So I would say we switch the order, and Marty, I would like to ask you to prepare your sharings, and I just leave a quick words on how we got to know each other. So Marty, you're a consultant as West Consultant, and you're also president there, and we know from the ICOLD. Of course, in an ICOLD webinar, this is not a real surprise, but we both are in the ICOLD Technical Committee J on Sedimentation Management. I think we met the first time 2 years ago. And I would say you're one of the people in that working group which really stick to my my mind, because you were really eagerly contributing to the discussions with your expertise and your also critical questions on how we can proceed and what input is very valuable there. So I would like you to I would like you to also give your knowledge to all the participants here, and I give the stage to you.
Okay, great, thank you. I'll go ahead and share. And let me know if you're able to see my screen.
Yes, we are able to see your screen.
Okay, great. All right, well, I'll go ahead. Yes, Valerie, it was great meeting you through Technical Committee J. Actually, I was chair of that committee for about 6 years before we transitioned over to Christian now, who will talk after. Yeah, under, well, while I was chair, we produced 2 bulletins, and I'll just encourage people who are on the call that if you're an ICOLD member, you're able to access those bulletins online. And so there's a number of bulletins there that have to do with sediment management. So please take a look at those. Today, I'm just going to present a couple of case studies of a few projects that I've worked on. And the main purpose of my presentation is really just to give you a brief overview, demonstrate a range of sedimentation concerns that we have to deal with in practice, and hopefully whet your appetite to get more involved in sedimentation engineering, as Lisa has told us with the Chengdu Declaration, and based on George's work also, we know that this is a huge issue worldwide. So I'll just start off. First example here is a dam in the United States. This is owned by the Tennessee Valley Authority. It's called Nolichucky Dam. The reservoir is already almost completely full with sediment. And for this particular project, we were asked to look at it mainly for environmental reasons related to dam safety. So you can see more or less where it's located in the eastern part of the United States in the state of Tennessee. And the purpose of this project was there's only a single gate, and they needed to remove it in order to perform some inspections. But when they did that, because the reservoir is already yes,
just a short interruption. You also
Sure.
seem to be frozen.
Oh, really?
And not only you, also your slides.
Okay. Let me.
I hope the speaker mode is not jinxed.
The screen is completely blank for me too.
Ah, George, hi.
Yeah, I'm back. Sorry about that. I hope I can come in now after Mark is done.
Yeah, don't worry. We switched order and Marty started to present, but now he's facing the same problem than you.
Yeah, it's strange.
I'm sorry for the technical issues we are facing. So I would suggest, George.
Yeah.
I would like to ask you again to start your presentation, and we hope for the best this time, and then we stick to the original. Yes.
You can see that now?
Now I can see your presentation. Yes, I see the PowerPoint.
Done?
Done. Yes, I see the first slide.
Okay. So let's hope this works now. Okay, so can you still see it?
Yes, I can still see it.
Okay. So like I said, I'd like just to remind us why we are doing reservoir sedimentation management from a more global point of view. And I want to cast it in the terms of sediment, climate change, and sustainable development. So I guess the first question that we need to ask is that what is meant by sustainable development? Okay, so if we go back to the Brundtland Commission definition, it says sustainable development seeks to meet the needs and aspirations of the present without compromising the ability to meet those of the future. This is a very succinct definition, and I think most of you know it, but I think what is really important is to recognize that the focus is on intergenerational equity. That means fairness between generations, okay? And the perspective, the time perspective is centuries, and I'll come back to that again a little bit later. But that is really a very important feature to recognize. So let's just first look at the resource. And the question is, how do we sustainably develop a resource? And as we all know, there are two types of resources on Earth. There are renewable resources and there are exhaustible resources. And according to Herman Daly, to sustainably develop a renewable resource, we must use it at a rate that is smaller than the rate of its regeneration. And if we work with exhaustible resources, we must make sure that the rate at which we use it is smaller than the rate of development of renewable substitutes. Then obviously, pollution should not exceed the rate at which the environment can assimilate it. So if we come back to water, let's just see how scarce a resource it is. And we can do that by comparing it to a sphere that is, relative to the diameter of the Earth, which is 12,830 kilometers. Now, if we take all water on Earth, everything, and we put that in a sphere, it will fill a sphere with a diameter of 1,390 kilometers. If we take all fresh groundwater on Earth, this is not working very well. There it is. If we take all fresh groundwater on Earth and put that in a sphere, it fills a sphere with a diameter of 68 kilometers. And if we take all river water on Earth and put that in a sphere, it's a sphere of only 16 kilometers. So you can see that's not a lot of water. So we have these two freshwater resources. We have groundwater and river water. So the first question we need to answer is which one of these have the greatest potential for sustainable development. And we can do that by looking at, for example, residence time. And for example, groundwater, the residence time for fresh groundwater on Earth is about 1,400 years. So what this means is if we would suddenly remove all the fresh groundwater on Earth, it'll take about 1,400 years for it to replenish to where it is at its current state. But in the case of rivers, if we would remove all the water in rivers in an instant, it'll take about 16 to 18 days for it to recover. So just purely from a gut feel point of view, if we compare it to the daily use of water, we can say that river water has a greater chance at sustainable development than what groundwater has. And if we look globally and we measure the usage of groundwater and the replenishment of groundwater, we find that we globally use 3.5 times more groundwater than what is replenished on an annual basis. So this then sort of confirms our gut feel that river water has a greater potential for sustainable development than groundwater. But the problem that we know is obviously that river flow is not constant, it's variable. And to reliably supply water, we have to create storage. That is an important element that if we're going to use river water on how to reliably supply it, both energy and water supply. So then if we go back to climate change and look at the aspects of climate change that may affect the availability of fresh water, there are two main features that are important. One is the mean annual river flow, and the other is hydrologic variability. Now, obviously, evaporation also comes into play, but I think that we can reasonably say that variability really has a significant role to play in the sizing reservoirs. So what I have here on the left-hand side is a map that gives you areas in the world where droughts last 2 years or longer. In other words, multiple year droughts. And in those cases, what we do need is large reservoirs. I grew up in South Africa originally, and South Africa doesn't have a lot of groundwater, but its reservoirs have to deal with droughts that are longer than often 7 years. So if we now just make a test and we say, let's increase our hydrologic variability with 25%. If we do that, then the situation changed quite dramatically, and you can see there are more places on Earth where the droughts longer than 2 years will occur, multiple year droughts. And for those of you in Europe, that is obviously something that you need to be concerned about, because currently, until recently, only Portugal and Spain had these multiple year droughts, and they have to size their reservoirs for that, but the rest of Europe not. Now, the question is, do we continue to add storage by the construction of dams? And if we look at the register of ICOLD, we see that it's actually true. This is the amount of storage that we added cumulatively since about 1900. And that looks pretty good. But one problem is, as we all know, is that reservoir sedimentation is the storage space enemy. Okay, so it reduces storage space. And to get some idea of how much it's reduced globally, we can look at a graph like this. At the bottom, we have time from 1900. We have on the ordinate on the left-hand side, reservoir storage in 1,000 cubic kilometers. And then on the right-hand side, we have per capita net storage. So this curve here, the one on top, that is the total storage that's being added through construction of dams. And then we have an estimate of how much that storage has reduced. In other words, this is the net storage remaining after 0.8% loss per year. And this is another estimate of 1% loss per year. Now, I must say the World Bank recently did a very detailed study of, country by country, where it is known how much storage is lost. And this 0.8% curve is most probably more reasonable. So what we're seeing is that we are losing more storage space to the reservoir sedimentation than what we're adding through the construction of new dams. And then if we take account of the population growth, we see that the storage per person has decreased significantly since about 1980. Okay, so this is not a good situation. How do we retain long-term storage? There are various reservoir sedimentation management techniques, and Marty will deal with that, so I'm not going to spend a lot of time on this, but essentially we can divide it into three groups. You can do upstream management by check dams and forestation. Check dams being the immediate assistance to replenishing it or reducing sediment yield. A very good case study for those of you who are interested is the Yellow River. China has done a tremendous job in the Yellow River by using a combination of check dams and forestation to reduce sediment yield. Then there are a group of techniques that known as sediment routing, and another group known as removal of sediment. So I'm not going to go through this. That is a topic of its own. But I think one thing for us as an engineering community of hydrologists and engineers to realize is that we have a choice. Either a reservoir can be a sustainable resource or a non-sustainable resource, exhaustible resource, and that's our choice. If we design a dam and reservoir by using reservoir sedimentation management techniques to retain reservoir storage, we can classify it as a sustainable resource, a renewable resource. If we do not do that by choice, we classify it as an exhaustible resource. So this is something that we do as developers of dams and reservoirs. The other problem is the whole issue, this whole myth of the time value of money. And that is something that really needs to be considered in more detail when we evaluate projects. This here is a cash flow of money. This is the investment to build the dam originally. Then you have operation and maintenance costs. And these are the benefits that decrease over time. But then at the end of the life of the reservoir, once it's filled with sediment, we have a duty to decommission the facility. And the thing is, it's a very large cost, but with the current economic assessment techniques, if we discount that cost, it doesn't do anything to the decision. So that is a real problem. And this gives you some idea of how the time value of money changes with time. Many years ago, a couple of years ago, the discount rate that was used was 12%. And you can see within 50 years, whatever cost or benefits come after 50 years is completely ignored. For a 6%, it comes down to 80 years. For 25, 2%, and 5%, you can open 5%, you can see it increases significantly. And if we look at 0%, obviously, then the value retains its full value. Now, this becomes very important when you look at intergenerational equity. We want to use very low interest rates so that we can account for both the benefits and the costs in the long term. The next thing is the fallacy of a design life when it comes to design of dams and reservoirs. Now, this is something, design life concept is something that's used in engineering all the time. And for conventional infrastructure, like say highways, this concept is acceptable, because a highway you can design and build, and after say 30 years, if the design life is 30 years, you resurface it again, and you can essentially use it in perpetuity. So this is an example of a project that is sustainable if you can continuously replenish it. But if you come to dams, once a reservoir is completely filled with sediment, the design life concept is not applicable anymore, because it's just unusable. You can't do anything to replenish it. So where we need to aim at is to have a perpetual life cycle. You know, we ensure that our planning and design can ensure that our facility lives forever. We construct it, operation and maintenance, we remove sediment on a regular basis, refurbish it, and that continues forever. So what I want to really emphasize here is the importance of the concept of time. And there's a very interesting book by Price, if you want to learn more about this. It's called Time, Discounting and Value, looking at how you assess infrastructure as large as dams. And there's a statement there that says, the future is all that remains of time, and the present is the vantage point from which we view it. So now, as a summary and conclusion to this presentation, there are some important factors for us to take into account. One is that we have to understand and respect the facets of time. Currently, the myth of a design life has a perspective of decades. The myth of the time value of money in economic analysis have a perspective of decades. Whereas we indicated that for sustainable development, we're looking at intergenerational equity, and the time perspective is centuries. And the perpetual nature of a life cycle management also in terms of centuries. So this is what we are aiming at. So the other thing is that we need to understand that we, as developers and maintainers of dams and reservoirs, we can decide what the nature of reservoir storage should be. Is it renewable or exhaustible? If we manage reservoir sedimentation on a successful basis, we have a renewable resource and reservoir storage. If not, we make a decision to make it exhaustible. And the last point is that reservoir sedimentation management should be considered for new dams, and this is, I think, becoming more and more practice. And also existing dams, we need to review them and then work from there to a concept of sustainable development. So Lara, this is what I have to say, and I hope this came across clearly.
Thank you so much, George. And I would totally agree with your last statement that the integration of sediment management strategies in new dams is becoming state of the art and is considered in more and more projects. And one of the, I would say, most stunning things someone told me was like, yeah, we will build a new dam here in Pakistan. It was in Pakistan. And if we don't integrate sedimentation management from the beginning, it will be full in 15 years.
Yeah, that's exactly right.
Yeah, so thank you so much.
Okay, you're welcome. I'll stop sharing here.
Perfect. And if questions arise, please feel free to already put it in the Q&A section. We will come back to it and answer it at the end of our presentations. I also received the message that Marty is with us again. So Marty, let's give it a second try, and I will give the floor to you.
I'm back. I'll try not to turn on my video here to see if that makes a difference, and hopefully it'll work this time. All right. So are people able to see my screen?
Yes, we are.
Yes.
Okay. Let me know if I freeze up again, but
I
I
do.
won't repeat what I've already started here. But the purpose again is really just to give you a couple case studies and whet people's appetite for interesting things in sedimentation engineering. I started to describe this project, which is the Nolichucky Dam. It's one owned by the Tennessee Valley Authority. It's mostly an overflow structure, mostly full with sediment, single operational gate that they have. And the problem with this one is that they needed to remove that gate to do maintenance as part of the dam safety exercise. And their worry was by removing that gate, they expected some of the sediment that had been deposited in the reservoir to leave and have higher than normal concentrations, which would cause all kinds of environmental permitting activities and expenses and delays. And so they wanted to know what the concentration might be of sediment leaving the reservoir and if they were going to have to go through this exercise of environmental reviews or not. So in this particular case, we did sediment transport modeling to look at mobilization of sediment and potential concentrations when the gates were moved. So we wanted to know what those maximum concentrations might be, how long they would last. We'd like to predict concentrations under natural high flows and compare that with concentrations expected during removal of the gate. And they were thinking that they might have to go in and do some dredging of the reservoir. And so depending on the outcome of our results, that could avoid the need to go in and dredge. So this is the lake. The name of the lake is Davy Crockett Lake. That's behind Nolichucky Reservoir. We were able to gather bathymetry, and this was a two-dimensional model that we did. So we had two different geometries, one with the gate closed, which is on the left, and one with the gate open, which is on the right. We were able to incorporate that within our model. And based on the results of the modeling that we did, we saw that it was very low amounts of scour that were expected, less than a meter, about 6 cents per meter, and very small volume, only about less than 10 cubic meters. And more importantly, the concentrations that we expected were pretty low, especially when compared to what we would expect to occur during natural events, say like a event that would occur roughly every 2 years. And so the modeling indicated that opening the gate would really just result in localized scour for a fairly brief period. It would be a temporary increase in concentration, which would be much less than existing conditions at natural high flows. Therefore, the TVA was able to avoid dredging, able to avoid additional environmental impact studies and the costs and time associated with that. I want to stop and just check real quick. Are you still able to see and hear me?
Yes, we are.
Perfect. Okay, glad to hear it. Let me just move on to the second study here. This is one that we performed on the Susquehanna River for Exxon Generation, a big power company. And for this one, it was interesting. It's a series of dams on the Susquehanna River, the biggest of which is the Conowingo Reservoir, which is downstream just before the river empties into Chesapeake Bay, which is a very important waterway on the east coast of the United States. So for this particular one, there was a number of different studies going on at the same time by different firms. And our role in this study was to develop really models for boundary conditions upstream. So we developed unsteady one-dimensional sediment transport models for the upper two dams of the lower part of the river, Safe Harbor Dam and Holtwood Dam. And it was really the purpose of this modeling was to aid in parameterization of the watershed, of the sediment yield, and also what the inputs would be, sediment inputs to the Conowingo Reservoir. There was some additional three-dimensional nutrient loading modeling that was going on in the reservoir, but they wanted to know what the sediment inputs would be. And so that was the purpose of this particular study. So Safe Harbor Dam, constructed in 1931, not terribly tall, 23 meters, but impounds Lake Clark. And then downstream from that would be Holtwood Dam, again, fairly old structure, 1910, not even as tall, and it impounds a smaller lake, Lake Aldred. And in the past, there had been a bunch of coal mining in this drainage basin. And so a lot of the deposits actually had a fair amount of coal. In fact, in the past, they used to dredge and then recover some of that coal to be able to burn it, which I thought was interesting. Not your typical use of sediments, dredge sediments. But again, we developed some hydraulic models and sediment transport models. The first thing we did was a hydraulic calibration. And this is just showing some of the model results, which are the solid line for stage and the dash line for flow, and then observations with the points, the black circles that are on there. So we felt like we had pretty good hydraulic calibration, and that's really a necessary first step for modeling. If you don't get the hydraulics right, there's no way you're going to get sediment transport calculations right. So we're pretty confident that it did a good job there. We also, as part of the sediment transport modeling piece, looked at calibrating the model. And the best we could do is that we had a number of ranges within the reservoir, and we were able to construct two different periods, one for calibration and one for verification of our numerical model, looking at volume change that was predicted via the modeling versus volume change that was observed by repeat bathymetry measurements of the reservoir. So in this particular case, looking at the calibration period, 2008 to 2013, within this period, there were several large events, including Tropical Storm Lee, which resulted in record flows. And what we have on the right are our results. The red line is the modeled bed change in terms of volume. And then you have observed change target range with our error variance. And that's because based on the equipment that they were using and the areas that they were and were not able to access within the reservoir, there was really a range of volumes that we thought were possible given the equipment that they use. And so what we were shooting for with the model is to have results that fell within that range. And so we felt pretty good about the calibration. And then we looked at a different period, 2013 to 2015, which was actually a low flow period. But within that, again, we were able to reproduce results in terms of volume change in the reservoir that were within what we would expected. So we felt fairly good about the model's capability to reproduce sediment coming in from the upstream watershed. And this is really showing a number of points on here divided up by different size classes of clays, silts, and sands. And basically our aim with this project was to create sediment rating curves that were be simplified. They wouldn't reproduce some of the effects that you see on here with the hysteresis in some of the curves, but it was something that would be easily implementable in the downstream model for the Conowingo Reservoir, the nutrient model. And so based on the data that was generated from the model, we were able to develop some rating curves. I should mention that this previous plot here is log-log. This one here, now we're just looking at normal scale without log transformation. And so we were able to come up with different rating curves for clays, silts, sands, and then total load. And this was basically our product that was provided to the modelers that were focusing on the nutrient loading for Conowingo Reservoir and ultimately Chesapeake Bay. So a few conclusions from this study. Again, our model was part of a larger study, but we were able to calibrate it and develop those rating curves that then were able to be used for loadings of Conowingo Reservoir and Chesapeake Bay. Okay, the last one that I have on here is some modeling that we did for the Army Corps of Engineers. This is in South Dakota in the upper Midwest part of the United States, as you can see on the map. This is on the Missouri River, where the Corps of Engineers has a number of main stem reservoirs all along the river. It's used for flood control, navigation, and power generation. And for this particular one, it was Missouri River near Pierre Yes, it's pronounced Pierre, not Pierre, Pierre, South Dakota, where it's the upper end of the Big Bend Reservoir. Because water coming from upstream was basically clear water, because impounded by the next dam upstream, the main sediment source was from the aptly named Bad River. And the Bad River is contributing sediment to the pool as a delta buildup. And basically, the Corps was worried about impacts on groundwater and increased flooding of communities in and near Pierre based on that reservoir buildup. So for this particular project, first thing we wanted to do was look at a future without any changes to see what we thought would happen with sediment buildup and impacts. And then as a second phase, look at several alternatives for moving sediment deeper into the reservoir. So again, the approach on this one that we took was hydraulic and sedimentation modeling, as well as geomorphic analysis. So this is just a snapshot, and I won't spend a lot of time on it, but this is a series of big reservoirs that we have on the Missouri River. And the one that's highlighted there, Big Bend and Lake Sharp, is what we were looking at with this particular study. So first of all, we prepared a sediment budget to determine local inflow amounts that we might expect. We analyzed the Bad River, developed a sediment rating curve, including size distributions. We looked at a calibration period, 68 to 97, and then a future period that we were going to use for analysis, which in this case was 97 to 2047. And that was, we developed hydrology that was based on some measured data. We also did some sensitivity of that hydrology in the sense of what if it was drier than normal or wetter than normal. We also did a calibration of the model where, again, it was computed results from the model versus measurements that were taken in the field from some permanently monumented cross sections that the Corps had. And here's an example of a calibration where, again, we're looking at sediment mass. So here's a cumulative sediment volume with distance along the river. And the model results are the diamonds, the measured results are the circles. And so again, we felt fairly confident that we were able to calibrate our sediment model to observations in the past. Therefore, we'd be able to use the model for our future predictions. We also took a look at plan form of the river and areas where there had been deposition, bank erosion, plan form changes in the river. And so over time, we were able to look at this and incorporate those findings within our model in terms of things that we might want to adjust with the model geometry or other parameters to be able to reproduce some of the changes that were observed during this time period. Okay, we looked at a couple different alternatives for moving sediment deeper into the reservoir, really moving that delta to reduce impacts upstream on water surface elevations, or WSEL is on here, and also groundwater levels. So some of the alternatives we looked at were, first of all, to lower the pool elevations on Lake Sharp. This would be extremely difficult to do, basically taking an act of Congress in the United States, but it's a hypothetical. We want to know if we tried 3 lower normal pool elevations, what that would do. And then we also looked at installing some spur dikes, basically to narrow the width of the river, increase the transport capacity, and hopefully move more sediment into the reservoir that way. So we looked at 3 different sets of dike lengths. And in here, the results were not as good as we had hoped, to be honest. Basically lowering the pool level, the normal pool elevation was 1420. So lowering it by a foot, which is about 30 centimeters, it lowered the pool elevation, but in terms of the change in the delta, it was minor, really just 10 centimeters or so. And then lowering it more had a greater impact, but again, not a huge impact. And just to cut to the chase, basically the spur dikes we found had really no impact, or we even caused things to be a little bit worse. And then I'll just, I'm not going to spend a lot of time on this, but I wanted to throw in one more example here. And this was the Milton Reservoir in the state of Montana. This reservoir was full of contaminated sediments some mine tailing had failed upstream and flowed into this reservoir, was, contaminated with all kinds of things. And basically, the plan was to using sheet piles to basically move the river to one side of the reservoir and then excavate the contaminated material in the dry. But as part of the activities, they expected water to be released with higher than normal concentrations. So this was another one where we were focusing on concentration of contaminated sediments that might have been released downstream. This dam was ultimately removed, by the way. And that is it. I have a couple pictures here of a project in Guatemala that I worked on a couple of years ago, where the top photo is before a couple hurricanes hit the watershed, and the one on the bottom is after the hurricane hit. So you can see the same bridge in both pictures. So I will wrap it up there, and Laura, turn it back to you. Thanks.
Thank you so much, Marty. Thank you for the valuable insights in the projects you were carrying out the last time. And I think I will save this question for the Q&A session. Be prepared. And now I would hand the floor over to Christian. Christian, you will give us an insight on the current work of the Committee J, because in the technical committee, we are currently working on the sediment management in cascading systems. And yeah, it's all yours.
Yes.
We see your presentation. It seems to work.
Yes, that was my first question. You see my presentation. I'm very happy about that. I hope also everybody can hear me. Welcome also from my side. I'm Christian Auel. I'm the chairman of the ICOLD Committee J, Sedimentation of Reservoirs. And today I would like to talk about the Cascade Sediment Management, the new bulletin we are preparing at the moment. Let me start with a picture I always use in many of my presentations. This is from the Elwha Dam in the US, which was removed. And this is back in 2012, where you can see the large amount of sediments deposited in the reservoir. And this gives a quite nice example on how much the sediments are filling the reservoirs. Just to briefly recap on the process, sediments are coming into the reservoir at every flood event, and they are accumulating. And time by time, the active volume decreases. And as you guys, I guess, all know, the storage decreases, which means the energy production decreases, irrigation and drinking water decreases. The dam safety is endangered. The erosion downstream of the dam will be severe because of lack of sediments. The ecological deterioration is large downstream, and last but not least, finally, the deltas, the river deltas, are declining because of the captured sediments. There was a recent study, worldwide, a look on sedimentation rates in 2022. We have between 10 and 25% of the reservoirs are silted up in average every country worldwide, and there was prediction to 2050 where we can see we have sedimentation rates between 25 and 50%. This fits quite well to the graphs George showed in the very beginning, so we have to do something about that. So if we ask the questions, are reservoirs sustainable? Well, without any measure against sedimentation, they are not sustainable in the long term. They're not sustainable in two ways. They're not sustainable for the reservoir volume itself, but they're also not sustainable for the downstream river. I don't go into detail on that graphic because I knew that George already captured that a little bit, but we have three different areas of strategies: the catchment to reduce the sediment yield, we route sediment through the reservoir when they're coming in, or once they're already inside the reservoir, we try to remove them. Just to briefly emphasize, routing the sediments is, from my point of view, the best option, is the most ecological beneficial option. So we always try to go for these options. This is a picture where I try to give an overview of the my personal favorites. That's in the catchment afforestation. That's very, very important in many countries of the world to reduce the soil erosion. Then, of course, it's sediment bypass tunnels. The people who know me a little bit, I worked a long time and I did my PhD also on sediment bypass tunnel. Beside the bypass tunnel, the sediment sluicing is the best option available in many cases. So diverting the sediments through the reservoir itself. And if we come to removing sediments, the continuous sediment transfer is a very valuable option. Having said that, let me please come to the new bulletin which we are preparing, and the outcome of this work we wrote in the terms of reference would be a best practice guideline for Cascade sediment management, and we will give a lot of examples from different countries. So first of all, we were discussing what defines a cascade. Well, simple as that, we need a minimum of 2 dams to define a cascade. And we said we need also sediment management in place already. And the dams must be somehow one system. There must be in a relation to each other. There has to be interaction between the dams. There have to be direct effects from one dam to the other. And there's a coordination to be needed between the operators. This is our definition. And these are the case study locations. We found quite many, basically almost all over the world. And I would like to emphasize on 3 a little bit closer today. The first one is in Malawi on the Shire River. Malawi is a landlocked country between Zambia, Tanzania, and Mozambique, and has a very large lake, the Lake Malawi. And from this northern lake, we have the Shire River here flowing into the south, and it has a number of hydropower plants along the Shire River. The first one is a Kamuzu barrage. It controls the outflow of the entire Lake Malawi, built in the 60s. Then we have Nkula hydropower plants in the 60s and 80s built, Tesani hydropower plants in the mid 70s, and a newly to be designed or planned a power plant at the moment, Patamanga power plant, and Kapitira power plant, which experienced a dam break in January 22. I will come on that topic in the next slide. This is an overview of Patamanga power plant, which is actually at the moment still in the design phase, and according to that plan to be commissioned in 2030, 55 meter high dam with 10 million cubic meter reservoir volume. We do have a lot of fine sediments in that river. There's an abundance of fine sediments. Here are some pictures from the catchment. We do have a lot of fines, and they are coming in large amounts during tropical storms, which occur annually. They create large pulses into the riverbed, and the discharge carrying the sediments downstream, they continuously reshape the riverbed, which you can see quite impressively here on that picture. And also within the hydropower cascade, there are several large sediment feeds from the tributaries, which are also significantly adding sediment load into this river system. That's a soil erosion map from 2020 on the downstream catchment of the Shire River. And we do see that the significant increase in the past decades, notably due to deforestation, and also the land use, which is notably due to the deforestation that increased the soil erosion and increases finally the sediment loads. The dams in the Shire River, they intercept these sediments partially or likely fully, and there's a 25% increase in sediment yield in a 50-year horizon if no measures will be in place. The newly to be built Patamanga will capture 100% of the sand and gravel and 90% of the fines. So like most of the sediments will be captured in Patamanga. Some words to the dam break in 22. Here you can see from upstream to downstream the reservoir, the dam itself, and then coffer dam here on the right shore. And this cofferdam broke during a cyclone in 22 and damaged also irrigation inward. And you can see here already the large amount of sediments accumulated in that reservoir. It's a 130 megawatt hydropower plant, and it's about 30% of Malawi's hydropower production. So they had a shortage of about 2 years of 30% due to that severe dam break. These are two pictures. Shortly after, you see the damaged cofferdam and the irrigation intake here. This is the view from the other side. This is the hydropower plant here and the dam itself, which is still okay. And with money from the World Bank, this power plant was rehabilitated in 2 phases. First, the cofferdam was reconstructed partially, and the water was diverted towards the power plant to produce energy quickly, and then the cofferdam itself was finally managed to build in 23. So now it's running again. There was also some sediment studies done by Deltares on that reservoir. On the left one in the middle, in the center here, you see the sediment accumulation in 3 years. On the right side, you see the same simulations, but with the upstream Patamanga reservoir in place. So you see there's a much lower amount of sediments coming into the reservoirs. Just the fines are still coming in because the Patamanga reservoir will capture quite a lot of sediments in the long term. Applied sediment management is not consistent along the Cascade. There are temporal dredging works. There is sporadic flushing operations. And here I would like to show 2 pictures of a flushing operation 3 years ago in Kula hydropower plants, where you can see the large amounts of sediments which are diverted into the downstream. Further future possible improvements. The Patamanga, for now at least, has not really a sediment measure in place, but there are ideas to reduce the maximum reservoir levels during rainy season and improve sluicing, and also during the flood season at Kapitira there will be new flushing operations, and of course also dredging works will be increased. Let me come to the second example in Switzerland. That's the Aare River. The Aare is a very long river initiating in the Alps, so the glacier, flowing finally into the river Rhine here at the border to Germany. We are looking at the very upstream reservoir Cascade, which has a number of reservoirs and dams. Let me focus on 3 of them. This is the Oberaar Lake, with the dam here, and the Grimsel Lake, which is a newly constructed dam, finished actually, not finished in that photograph, but finished last year, and downstream the Reservoirs Lake. So these 3 lakes are connected to each other, and it's one system, one cascade. So there's a high sediment yield from a glacier, so predominantly fine and grain sediments. Main concerns of the company KWO is a blockage of bottom outlets, loss of storage, of course, and turbine abrasion from the fine sediment is also an issue. So the Grimsel hydropower cascade, the 3 reservoirs, they have a very high trapping efficiency. They trap almost 92% of all sediments. The measures which were applied is annual pressure flushing, which is just done at the bottom outlets, and it's just a funnel which kept free for security, and aperiodic drawdown flushing, which can be seen here in the 3 lakes. Commissioned Oberaar in 1953, partial drawdowns were done basically 3 times up to today. And Grimsel, commissioned in 1931, there was 2 emptying phases in the 40s, 50s, and 70s, and 2 partial drawdowns in the last 25 years. The Reservoirs Lake was commissioned in 1950 and 3 to 4 times emptied. So this is done, but not frequently, and mostly due to construction works. So the modern strategy, the new ideas and new operational principles of the operator are to switch from full emptying to sequential partial drawdowns that route sediments downstream, operate in a sequence from upstream to downstream to maintain sediment continuity and minimize operational downtime, and to use 3 phases, basically pre-flushing, where monitoring is being installed, the permits are done, and baseline ecological assessments are done. The flushing or sluicing event itself is a controlled drawdown and sediment routing, and a post-flushing where the ecological restoration will be monitored, sediment surveys will be done, and rinsing flows, clear water flows will be going through the river system. There will be improved monitoring, and finally, also very important, the stakeholder coordination between the different stakeholders there. Finally, I would like to give an example from a study in Japan, where I also worked for 2 years in Kyoto University. The Japanese have already in place a very good cascade system. One of these cascades is the Kurobe River, which is in the western part of Japan on the west coast, the Toyama prefecture. The Kurobe River is very steep, with the highest dam in Japan being the Kurobe Dam. Very large reservoir, and a number of downstream reservoirs, in total 5. I would like to focus on 2 of them. The one is this one here, Dashidaira Dam from Kansai Electric, 80 meter high, 9 million cubic meter volume, 100 meter high, 25 million cubic meter volume, the Unasuki Dam, from a different operator, from MLIT, that's the Ministry of Land, Infrastructure and Tourism. So it's from the government, and this is the private power company. What do? They have a steep basin, extreme sediment yield, and these 2 dams, they operate, the first ones that in Japan also operating in a cascade, they coordinate the annual sluicing since the early 90s. The trigger threshold when they start operation in the rainy season is the 300 and 400 cubic meter per second respectively, and also they do a clear water rinsing after the flushing event. The long-term outcomes is the stable sediment balance, sediment continuity. They have very active sandbars, changing morphology, and also ecological advances since they're doing this. These are 3 pictures I'm showing now from Unasuki Dam. So prior to a flood, mostly in fall, the water level will be lowered, the reservoir will be emptied. You can see here the clear water going through the bottom outlets. At a certain point, these side outlets here, they will be opened, and the sediment-laden flows will be diverted. The reservoir is completely empty and flowing in free flow. This is afterwards, it's filled again, the gates were closed, and the clear water from the upper areas is rinsed downstream. That can be done annually because there's a lot of rain, first of all, and they also have the largest reservoir upstream, so they can quickly fill back the Unasuki and Dashidaira reservoirs. So let me show you this slide. This is the Dashidaira reservoir, so the upper one. The Japanese do sediment measurements every year, so this is the sediments accumulating in the reservoirs. The reservoir volume was 9 million cubic meters, so it would have been already full in 1999, but since the early 90s, as I said, there were these measures in place. In the early 90s, it was at the wrong time of the year. It was mostly in spring when no flood events occurred, and there was a large typhoon hitting the area, and afterwards they changed to fall, and since then all this green area, this is basically the real deposited sediments. This is calculations from a 2D modeling. Almost 90% of the sediments are routed into the downstream through this reservoir. This is showing very clearly the very effective sluicing technique of this Japanese reservoir. So let me conclude with 3 take-home messages I would to convey. First of all, reservoir sedimentation is, from my point of view, one of the biggest, if not the biggest, challenge in the 21st century for us as hydraulic engineers to ensure sustainable reservoirs. There is a number of countermeasures available, but they must be applied more frequently and planned from the very early beginning. And coming to our bulletin, a coordinated cascade management is key from my point of view and must be applied for consecutive reservoirs in a river system. That is the most important take-home message I would like to give. And with that, I'm very happy to welcome questions, and I give over back to Lara. Thank you very much.
Thank you so much, Christian. And yes, I totally agree that the next decades and the next time it will be more and more important to put the focus more on the sediment management, and also to shift the focus from the from a reactive point of view and treating the reservoirs individual, and going more to more coordinated interventions, and that it is more than important to develop a long-term strategy. So thank you. Thanks to all the speakers. I just want to appreciate you all stick to the time. So we have we are really perfectly in time when now I want to open the Q&A session. So I think we could give it a try to reactivate our cameras, because right now we don't have to share any presentations. And we already collected some questions in the Q&A section. So to all the participants, if a question arises, don't hesitate, put it in the Q&A session. We will moderate it. We will take your questions to our speakers. So if you want a specific presenter to answer your question, or if your question goes to one specific speaker, put the name next to the question. So the first question I want to hand over was asked by Giovanni Schicchi. And George, this question goes to you. It is about how we could integrate the sediment management aspects in the standards and guidelines regarding the design life concepts. So could it be integrated in the current used perspectives of the design life of reservoirs, or does it need new regulations and new ways?
You know, like I said, I've been involved in reservoir sedimentation management for, what is it now, 50 years, and was promoting technical compliance and stuff. And it was probably about 10 years ago, I realized that to make progress, you really have to go to the policy level and regulation level. So, I know for the last 15 years, I think I've been talking about the concept. But what we did in the World Bank, we developed a document to assist governments to develop policy for sustainable development of reservoirs. So for the answer to the question is regulation and policy, and one need to convince politicians and bureaucrats that this is an important issue. Like I say, I believe, you know, I've had some health problems, so I was not attending conferences for many years, but I was in Chengdu this year, and I was really happy and pleasantly surprised that the concept of reservoir sedimentation management had a much higher presence in the presentations in the general conference. So I think we're getting there, but I'm giving a long answer here. Yes, regulation and policy is a big issue.
So one more question to that topic from my side. How long do you think will it take for like major changes or major adaptations?
You know,
decade more?
my experience in, and I think we're along the way, but my experience in just introducing a new idea is to, for about 10 years, repeat the same message over and over and over. And eventually people say, oh, that's not a bad idea. So it is a consistent pressure from everybody and consistent reminder of the importance of this to go ahead. Like I say, you know, I was really happy in Chengdu when I saw the presentations and what has been done in reservoir sedimentation management. Obviously, we need to do more, but we need to keep on spreading the message. That's important.
If I could add to that, George, you know, I think what I've been seeing, and I have to admit, you know, I was in primary school when you started, maybe, so you have a few years on me. But I think the mindset has been changing, especially the younger people. You know, as Lisa presented on the Chengdu, and as you mentioned, you know, I think, you know, years ago that never would have happened. And I think the mindset has really been changing in the profession. I think with the younger people coming up and realizing, you know, climate change is a big deal on top of the problems that we already have. So I'm hopeful. I see progress.
I am, you know, I know when, as a young engineer, if you mentioned the words reservoir sedimentation management to the dam designers, they would immediately push you away and you never talk again, you know. So it is not like that anymore. So.
Thank you. Marty, I see you're eagerly answering questions in the chat. I really appreciate that. I want to pick up one. I want to pick up one question again. It was asked by Amanda Carvalho, and she was asking, at what point does sedimentation begin to pose a risk to dam safety? Which you already replied to that, but would you please give some comments on it?
Yeah,
because I think it's very important.
In my opinion, it's very project specific, and for many projects that I've seen, and perhaps George can comment on this also, you know, it's not an immediate issue of dam safety where the structure is impacted or might fail with additional loading, but it is an issue for the sustainability of the project. So does it matter if the dam is, you know, completely safe if you don't have any storage left, right? And I think some of the projects that I worked on, you know, they were dam safety projects, but we looked at it and sediment really wasn't an issue except for maybe some, you know, abrasion or things like that. But the main issue was just the viability of the project itself.
Yeah, you know, the thing is, I think what, like I say, another thing that encouraged me is I'm currently sitting on a panel of experts for Rogan Dam. And long-term reservoir sedimentation is a major feature that we're looking at. And as far as dam safety is concerned, you know, your storage capacity and the ability to attenuate floods is continuously decreasing. And the system of spillways that we are developing at the moment takes account of that. So that is, it's heartening to see that, but that is a dam safety issue, is overtopping, potential overtopping if you cannot pass the flood, you know.
Maybe Lara, if I can also quickly add to that, what I presented from Switzerland, I think it's also quite common to at least flush close to the bottom outlets. The bottom outlet has to be in operation. If not, basically you cannot empty the lake anymore, and that it's in many countries a concern. So this is done, at least in that example, annually, but it's just a flushing cone because you don't lower the reservoir level, so you get very close to the bottom outlets, you get some sediments flushed out. But that's important because if the bottom outlet is clogged, then basically you have a major safety issue.
I can't tell you how many projects I've looked at where there is a bottom outlet, but nobody uses it. In fact, sometimes they like weld it shut because everyone's afraid that if you don't start using it from the beginning of the project, then you have sediment against it, and everyone's scared that once they open it, they're not going to be able to close it again. So they just don't use it at all. So why did they go to the trouble to build it it never gets used, but that happens pretty frequently, at least that I've seen.
Yeah, agreed.
Yes, cemented bottom outlets are a universal issue.
Yeah.
Maybe just connecting to that question. I see another question in the Q&A, and it's about concerning the sustainable dam design. What are the main aspects we should focus on? Should we prioritize flushing capacity, so a large bottom gate, or maybe on a forest cover within the watershed? George, this is a question for you, but I think we can spread it out with the whole discussion group.
The thing is that firstly, that is project specific. It depends. I know if you want to flush, you must have the right reservoir shape. You must be able to draw it down, flush it, and you must have a hydrology. It can fill it up quickly again that you have water for the next season, as an example. I think the thing is, so they are, and I will promote the RESCON software that we've developed through the World Bank. The first one was in 2003, was a spreadsheet, but now there's a really nice package that you can get from the World Bank for free that will help you to, at least at pre-feasibility level, identify which of these techniques, all these techniques are the most desirable to use. And you can do an economic analysis, and you can do a preliminary climate change impact assessment and stuff like that. So that is something that Nikos Efthymiou was, I did the architecture, but Nikos developed it, Nikos Efthymiou. So that is really something I can recommend if you want to study these concepts, that you do that. As far as catchment management is concerned, that is a very difficult issue because it's very costly and it's not always certain how effective it is. As far as I know, and Christian and Mari and you, Lara, or the rest of you must probably give other examples, but there's a very good example in the Yellow River, where they, in the uplands, where they applied techniques to actually reduce the sediment load in the Yellow River. Now, the procedure was they built thousands of check dams, and they had these farmers do that until the farmers decided this is no longer an issue for them, but they literally built thousands of check dams. That's the first thing, because that stops the sediment immediately, and then they revegetate it after that, because the revegetation is the long-term strategy, and the check dams is the immediate response that you require. I think you could do that in a country like China. I do not know if you can do it anywhere else, right? Or, it's most probably less desirable or less feasible to do it somewhere else. To give you an example, we are currently, but this is working, I'm also on Rogan Dam, and Rogan sediment load is very high, the Vax River, but it's really high because of a lot of debris flows. And we are looking currently at the catchment with debris flows, and it is debris flow because it's very steep slopes, and once it starts to run, I mean, debris flow is different to normal sediment transport, and to control that is very difficult. So we are looking at that, and it is, for me, is to rather try and eliminate, not to respond to it and try and protect your infrastructure in another way. But I'm talking too much, but I think the two things are not vegetation only, but check dams play an important role.
Thank you. I think you don't talk too much. There's never too much when it comes to talking about sediments.
May I share a strange sediment management?
I'm curious. Yes.
So in the case I showed in my almost last slide about this Kirkini Lake in northern Greece, That was built in the 30s because the sedimentation carried by the river was threatening to block the river itself. So instead of having a natural lake that would be created by sedimentation, they created an artificial lake. And it also serves for flood purposes. So one would consider that this lake would be very soon full of sediments and no longer used, since that was the initial purpose. However, people, it is now regulated. Before it was not regulated, but now it is regulated that they give permissions, environmental permits for contractors to go and get sediment from the delta or upstream of the lake. And this, because I've seen over a decade the progress of the bathymetry, and it seems it works. Just sharing this experience.
Yeah,
Thank
well,
you.
I mean, Cristiano's probably can talk about the Miwa dam and stuff. That's exactly what they do. They have check dams upstream, and they have construction companies coming in and removing it. You know, it's the thing is, you know, we this is also about 20 years ago. I was working with Saturo Ueda in Kenya, and we did a complete study of the whole country, all the dams, and recommended Mwashi Dam in Mombasa, and it's now eventually being completed. But to manage sediment in that, we proposed to have 2 check dams upstream. But the important thing is you have to manage it. You have to empty it out, and otherwise it's useless. You know?
Maybe just like a quick note on that, Lara. Yes, if it's possible to use the sediments at a certain point as a construction material, of course that's done also in Switzerland and in Japan. For example, Miwa Dam, there's a huge amount of sediment used for concrete, basically. If that's possible from the grain size, that's not as sustainable from the ecologic point of view if you divert them downstream. So if you remove everything, I would suggest that's not really sustainable anymore, but partially that's of course it could be a win-win situation.
Yeah, but also one can I think in the Korobe River also that way downstream they build sediment banks in the river so if the river flows, then it re-entrains the sediment and restores the ecology. You know, but yeah. But I think Miwa, Christian, also in Miwa Dam, don't they deposit some of that? They excavate sediment and they place it downstream in the river, I think, if I recall.
Yes, they do have a lot of options, basically almost everything. They have check dams in the catchment. They have a sediment bypass tunnel for the fine sediments. They have some area where they capture the sediments, they truck them downstream and replenish it. Yes, and partially they use it. Yes.
Yeah.
There's a lot of sediment production in Japan. So.
Let's continue. I have a question to you, Marty. It's about the modeling and the case studies you presented. So I have a 2-in-1 question. So first, how were the sediment characteristics, particularly the grain size distribution, the concentration, and the sediment deposition profile in front of the gate, were implemented in the model? And how much data do you need for the calibration and validation of those models?
Yeah, so I think I'll start with the second part first, where the data is as much as you can get, because typically we never have enough. In fact, there's been several projects where we start with almost no data, and of course there's no budget or time to go out and do a field campaign to collect data for 10 years. Everybody wants an answer now. So there's a lot of uncertainty even when we do have calibration data within sediment transport modeling. So we always have to do sensitivity analyses, even if we do have a good amount of data to work with. And so that's something I didn't really have time to present much here, but that we always do sensitivity analyses on the results. because a lot can change in terms of roughness that you assume, sizes that you have, type of transport relations that you use in the model, hydrology that you use as input. There's all uncertainty in all of those factors. And so we usually take that into account to do sensitivity analysis. In terms of the first part of the question with the concentrations and bed gradations and things like that, basically for inflowing concentrations, we develop data coming from upstream based hopefully on recordings that we might have, stream gauge. If not, we come up with some estimates, again, based on existing sediment transport relations of a sediment rating curve, solid flow with liquid flow. And then we always have a campaign to collect sediment data. In the case that I presented with Nolichucky, there was a question on that. I mean, basically, we had a sampling campaign where we had, I think, about 10 samples that we had in the reservoir and on the banks of the reservoir, and developed sediment gradation curves. Based on that, we defined 3 different material types, basically sandy, sand, silt, and clays, and then implemented that in the model for various zones of the area that we were modeling. So I don't know if I answered everything that was in the multi-part question, but if not, let me know.
I think you did. I think you did. I told you I saved a question for the Q&A, and it was about the case study you presented the last, where you said like there were like 5 million cubics of sediments in the Milton reservoir, but which were contaminated highly by arsen. So my question is, what did they do with those 5 million cubics? That's a lot.
Yes. Yeah, it was a huge project, and in the US it's called a Superfund site, which had special funding associated with it. But basically what they ended up doing was excavating in the dry, where they basically emptied the reservoir, they moved the river to one side of where it was in the reservoir, and then they went in and they excavated everything that they could. Then they moved the river somewhere else, went in, excavated some more, but all that material had to be hauled away and stored in landfills. So you imagine how many truckloads that was to move that amount of sediment.
Yes.
So yeah, it was a huge project.
Yes, I'm currently involved in a project, and we try to deposit like 100,000 cubic meters of sediments. And I'm running from landfill to landfill and checking, hey, I have a huge quantity of sediments. Do you want them? And they are all like, no, absolutely not. So I cannot imagine finding a place to just store 5 million cubics. So
it's a big problem, even in reservoirs that are not contaminated like that. And there's a case that George is familiar with that I contributed to the upcoming Cascade Bulletin too, for the San Gabriel River in California, where they have deposition there. And for some of the removal they do, they have to truck that sediment to landfills, and it's not contaminated. It's fairly clean sediment, but because of the environmental regulations that exist here, they're not able to say let it go down or take it to the beach or something else. They have to put it in landfills, which is extremely costly, and then you have all the environmental impacts and pollution related to the trucking. So it's just kind of a mess. I wish we could educate some of the regulators more on sediment and how it's a natural process and not a pollutant.
Exactly.
Yes. In Europe, we are facing the same regulatory tasks, I would say. So I think in the next decades, we have a lot of work to do to make sediments to do like a total makeover of the image of sediments.
Yes.
I think this would be a great step towards a more sustainable sediment management.
Yeah, absolutely.
I see one more question. I mean, I see many more questions, but the one I picked as next is what would be a good first step towards a sedimentation management strategy? So I think we all know every project is unique and every reservoir is its own case. But what is your opinion? I just ask it in the group or in the round. What is your opinion? What would be a good first step towards a strategy?
I put in the answers, measurement. Until you know how much sediment and what type of sediment you have coming in, it's hard to come up with good management strategies. So a lot of projects, even in the US with government-owned projects, there's some projects that have never had a sediment survey done. And so if you don't know your rate of sedimentation, you don't know if, where you have a delta, you don't know the material or how much is coming in, say on an annual basis, it's hard to devise strategies very well. So I would say measurement up front is really key.
I was about to say the same. Thank you, Marty. Yeah. I guess that's crucial. Yes, without any bathymetry, you cannot do anything. But then it depends on the size and the area of the reservoir, of course. Bypass tunnel and also sluicing operations are like more smaller reservoirs or like medium-sized reservoirs. At a certain reservoir size, I guess George maybe can talk best about that. That's very, very difficult to find suitable solutions. The smaller reservoirs, it's much easier.
I think Lisa has a hand up there.
I would go maybe one step back. Monitoring is always wishful. Is the best thing to have the measurements, but even before measurements, maybe at the hydrology stage of each project, a sedimentation estimation could be made with empirical methods, and which would need to be verified and calibrated with measurements. But when the concept of the project is at an initial stage, maybe these are not available. So better having something than nothing.
I think, also if you look at new dams.
To start thinking about it, yes.
If you look at new dams that you want to build, a large project takes several years before it gets even moving on the actual design. And I think what one should do is exactly what Marty and Christian and Lisa also say is you have to, when you start looking at a project, start it immediately with monitoring. But I think the next thing is, which I think was raised during presentations here, is that you have to plan right from the beginning for sediment management. Don't just, the dam engineers, they get into this concrete and embankments and stuff, which is important. But I think the thing to remember is that the dam is only there to create storage space, a reservoir and head. And if that is not there, the project is done. You can be as happy about keeping your dam up there, but you don't have a project anymore. So I think the thing is planning right from the beginning. Day number one, you have to look at that.
Yeah, I totally agree. I would say we have time for one or two more questions. And I pinpoint one because I think it's kind of interesting and I'm not sure if we have an answer to that, but I would like to put it into discussion. So it's about sediment flushing. And the question is, has regulation for sediment flushing in river cascades advanced? And is there any technical consensus on the concentration rate of the released sediments?
I think, what I understand is that more from a regulatory point of view, the question is focused on that. I think for me, it depends on the country you're in and how advanced the country is. Currently, I'm working with a reservoir with Nikos Efthymiou in Colombia. And Colombia is way ahead of most countries in the world in terms of regulating reservoir sedimentation management. They are, the utilities are expected to do it. Okay. And so, obviously you need then to convince the environmental group or environmental department that you can do it safely. But there are publications where you can, for either salmonid or non-salmonid fish, you can calculate what the allowable sediment concentrations are, and you just work within those levels. If you flush, obviously, you're going to have high levels of sediment concentration, but the duration of it also is important. If it's a short duration, it's not a big issue. And then, like Christian indicated, like in the Karube River, afterwards they flush it with clean water again, and so their strategies are developing, and like you say, it's regulation and policy that is in the end going to determine what we cannot do.
It depends a lot on the river that you're working in and the species there. So there's many species, for example, in the Colorado River and Missouri River in the US, which carry high sediment loads, and the species are adapted to that. So if it's not, I won't say it's not a big deal, but up to a certain concentration, the species are already used to high sediment loads, at least at certain times of the year. Other rivers, it might not be that case. So it's somewhat specific from the species that you're dealing with. And there are studies people done in the literature about, what permissible sediment loads would be for certain types of species. But a lot of it goes back to regulations. I've worked in countries that I won't mention the names here, where there's basically no regulations, and people will flush very high concentrations, which obviously has impact on the species downstream. But there's a lot of other countries that have limits as to how much they will allow the concentrations to be, just because of the impact on flora and fauna.
Yeah. I recall, many years ago, I think you've since worked on what Gavin's point had to be, was issues of can we flush it? Well, the answer was yes, because there's a lot of sturgeon downstream and they like the sediment, so.
Mm-hmm. Yeah.
Maybe to add on that also, in the discussions in the German authorities, for example, it's still very difficult to flush or sluice sediments. But we have to move to the idea that what I try to emphasize on the sediment routing is the natural event. It's a natural flood, and we divert the flood into the downstream. So in the best case, in the theoretic case, there's not a higher sediment concentration than in the natural flood event. Of course, if we accumulate the sediments for 1 year or more than 1 year, there's a little bit higher amounts of sediments if we sluice sediments to the reservoir. So it's a mix of flushing and sluicing, but the idea should be that we do not have higher concentrations than in the natural flood. And then it should be also, this is the baseline, it should be okay for the aquatic environment. This is at least that I try to move it into that direction, the discussion.
That makes sense.
Mm-hmm.
I would like to ask one last question, and it's about the ResCon 2 tool. And the question is there any feedback whether it is widely used?
Well, I recently had a sort of just a social conversation with Nikos, and he told me that Gerrit Pesson, I think it was on Capachia River, on the Sire River, that he did ResCon and he did conventional modeling, and they're very close, the results, so how widely is it used, I do not know, but Nikos is used in a number of projects. I know that, obviously he developed most of it, but I think that the general feedback we get, it's pretty good. I applied it to Rogan now, and there's only one potentially feasible technique, and it's density current venting. And HR Wallingford is currently doing the study, so we'll see how close that comes out. But I cannot answer the question numerically how many people are using it, but it has been successfully implemented, put it that way.
Nice. So congrats for creating a tool which is used.
Yeah.
Thank you so much for your questions, and thank you so much for the good discussion we had and all the answers we could give to our participants in the audience. And now I'd like to go to the last part of our webinar, the closings. And I just want to mention we will have this webinar uploaded on the YouTube channel of the Young Professionals. We have a great collection of webinars on there and good information we collected within the last years. That's not the only thing we do as the Young Professionals. And for the closing, I will hand it over to Matea. And just to be sure we won't have connection problems, I would like to ask us to turn out the cameras, to turn it off.
So good afternoon, good evening, good morning to everybody. I'm gonna be brief in closing. I'm gonna share the presentation, and hopefully this is not again a chance to have technical issues. Before I will start with saying, first of all, thank you to all of the presenters. I really enjoyed your presentations, and I'm really happy to see that the Q&A session was full. And I really enjoyed watching how the presenters, when you read and hear a good question, how your faces light up, and how then you build it up on each other's answers. It's like inserting a coin into the vending machine. It was really fun to watch, and I enjoyed it. So thank you. And thank you, Lara, for moderating and organizing this webinar. You did a great job as well. So now some technical informations regarding the ICOLD Young Professionals Forum. First of all, yes, we work with the ICOLD, International Commission on Large Dams. We are a forum that was formed and established in 2011, and we try our best to be active ever since. Our mission is we are targeting early career professionals, so the professionals that are in the beginning of the career who are under 40 years of age, and our aim is to creating opportunities for mentorship, networking, knowledge transfer, and experience sharing. We also aim to inspire young professionals to become active in their national committees, to become active in ICOLD, and of course to be active in the dams and reservoir sectors, because the challenges we are having in this sector will not disappear overnight, as you were able to see today. Our main activities are we meet in person at least once a year at ICOLD events. We organize workshops, virtual meetings, mentoring lunches. We manage a LinkedIn group. We organize webinars like this one today. Usually these webinars have a lot less technical issues that we had today. And we manage a YouTube channel where we primarily post the webinars that we organize and also the webinars that are shared by us by other technical committees in the ICOLD. The young professionals of ICOLD are led by the board members. It's 7 of us. Our term is for 3 years, and all of us are nominated and supported by our national committees and elected during the in-person meetings at ICOLD events. So in the next meeting, which will happen in Guadalajara next year in May, we will have 2 open positions. And if you feel like you would be a good candidate, if you know a good candidate, be alert. We will open the call in March and check out what is required for you to become a candidate on the elections list. We serve as an umbrella for national young professional networks. To this date, 33 countries have their own national networks. If your country is not among the countries listed here, if you want to change this, you can contact us. We are happy to help you and support the formation of your national committee, National Young Professionals Forum. And the moment you are formed, just let us know at the same time, and we will accept you and involve you in our activities. One thing that is also something we need to emphasize: every year at ICOLD conference, the Young Professionals Awards are given. So if you send a paper to the ICOLD conference, if you are a first author and you are young professionals, then you have a presentation. There is always a committee who evaluates all the contributions by the young professionals, and the best 2 or the best 3 are also awarded with the YPF award. So until today, 28 professionals have been given and granted this award. We just closed a call for the with the dams and dams initiatives. I'm a little bit tired, so I'm messing up the names. I apologize. Dams and Sustainability Initiative. So we just closed the call. We received a lot of very good applicants, which are under evaluation. At this point, I would just like to say, given that we received such a good feedback for such a call for the young professionals, you can expect similar calls for different initiatives in the future. So again, stay tuned, monitor what we do, and if it's something that is in your field, make sure to apply. So practical information, it was already mentioned, we have a YouTube channel, we have a LinkedIn group, join to both of those, and we have a web page under the ICOLD domain. So if you're interested to learn more, also our contact information is there if you want to reach us. And this webinar, as well as the rest of the webinars, will be recorded and it will be posted in our YouTube channel. So if you're interested in the content, if you want to review today's webinar, it will be available over there. And with that, I would just like to say thank you. Thank you for participating. Thank you for your patience, and see you in the next webinar, which will be somewhere in the beginning of the next year.
Nice. Thank you.
Well, thank you very much. That was excellent.
Thank you
Yes.
also from my side.
Thank you to all of you.
Yeah. Thank you so much
Yeah.
for being speakers. And
Okay.
thank you to the audience to asking such great questions.
Okay, thank you very much.
Great
Bye.
event. Thank you. Bye-bye.
Thank you.
Bye.